limitations of regression. Okay, so let's look again at the scatter plot of gestation and birth weight. We had 10 babies, and the gestations length of pregnancy ranged from 32 weeks up to about 42 weeks. Birth weights from about 64 up to 122 ounces. And they're fairly close to a straight line. But and that's indicated in green here. What happens if we extend this line down to 0 weeks? We can see that this line represents predicted birth weights, but we can see that after 10 weeks, for example, our predicted birth weight is a negative 50 ounces. And I mean, that would not be a birth weight. The weight of the fetus after 10 weeks is predicted to be about negative 50 ounces, and that does not make a lot of sense. And the problem is that growth with unlimited food supply tends to follow an exponential pattern rather than a straight line type pattern. And that means for an exponential pattern, that means that the slope keeps getting steeper. Here you have almost slope 0. Here you have a slight positive slope, and here you have more steep positive slope. So with a exponential type of pattern, the slope keeps increasing as over a period of time, over a period of increasing x values. So so we can still use this equation for babies born after 32 to 42 weeks. Baby born in that time period is a pretty good fitting equation. But this equation is not going to be very helpful for determining the weight of a fetus between 10 and 20 weeks after conception. It's not going to be much use for that. We could, if we had the data, we could do a different straight line for that time period. If I had a ruler here, I did have a ruler. I just had a ruler. Here it is. Now we could do a different straight line for that time period and get a pretty good fit, but we can't use the same straight line here. So if you're using predictions to make, if you're using equation to make predictions outside the range of the original x values, that's called extrapolation. And sometimes you can't avoid doing extrapolation, like if we wanted to let's say, for example, predict the world population in the year 2100 or something like that. Then we don't have data from the year 2100, so we're going to have to extrapolate. There's no other way around it. But so sometimes you can't avoid it. But if you do extrapolate, you just have to be a little bit cautious about it, and maybe keep in mind that this is an extrapolation. It's not. It's not something that we actually have data for. Now if you take a different statistics course, there are ways of fitting an exponential equation to this set of data, but we're concerned only with fitting straight lines, so we're kind of limited in that way. Okay, so yeah, there's it's besides growth with unlimited food supply, another sort of application of exponential equations would be in the growth of money at a fixed interest rate. So if you invest money or if you borrow money, after a while you're earning interest on the interest, or you're paying interest on the interest. So it's not going to be a constant rate of increase. It's going to be you're going to have an exponential type of a pattern. Okay, so there are at least two types of outliers for two variable data. If the point has an outlying x value, that's called a high leverage point. So this baby that was born after 32 weeks is its x value is much different than the other. The other babies were born 39 to 42 weeks. So this is an outlying x value here, this 32 weeks baby. So that's called a high leverage point. It's going to have in this case, it has a big effect on R. If we take out that point there, it doesn't have much effect on the slope, because without that point, it looks like we pretty much have the same line without that point. So it doesn't really have much effect on the slope or the y-intercept, but it does have a big effect on R. The correlation coefficient, if we compute R without that point, we get a correlation coefficient of 0.7, which is I would describe that as a moderate positive correlation, compared to a correlation coefficient of 0.9, which is I would describe as a strong positive correlation. The slope and the y-intercept are pretty much the same. There's not much change there. The other type of outlier would be Yolanda had above average gestation, a below average birth weight. So Yolanda this is probably Yolanda here. This point here is probably Yolanda. It's a little bit further from the prediction line than the other values. And actually, when you compute the residuals, you're not going straight toward the line. You're going vertically. So this is when you compute the residuals. You have to go in the vertical direction until you reach the line. So that's going to have the highest residual there, that Yolanda. So that's the other type of prediction error. It's when the x variable, it's an unusual x-y combination. So if you have a above average birth weight and above average gestation, below average birth weight, or vice versa, you're going to have you could have a point that has a big effect on the statistics. So if we compute the statistics without Yolanda, we have a higher correlation coefficient. We have 0.95 instead of 0.91. We have a different y-intercept, -125 instead of -109, and we have a different slope, 5.86 instead of 5.42. So Yolanda had a big effect on all three of them. I would call Yolanda an influential point. It's not a high leverage point necessarily, but it's an influential point because it affects our texts. Some texts say consider if it affects the slope. So I'll use that definition. If the point affects the slope, that's an influential point. So Yolanda is an influential point. If you look at the sum of squared residuals, Yolanda's had the biggest contribution to the sum of squared residuals. It's 165. That was Yolanda, her contribution there to the sum of squared residuals. That was the total sum of squared residuals 417, and that was more than 1/3 of that. It's from, maybe about 40% of that was from Yolanda, 165. That nobody else came close to having that. Okay, so we saw that one of the limitations of regression is that the curve might not be the overall pattern might not be a straight line pattern, and you have to be careful about extrapolating. We also saw the effects that outliers can have and different types of outliers. Another thing to be cautious about in regression and correlation is jumping to conclusions about cause. If variables A and B are strongly correlated, it might be that A causes B, it might be that B causes A, it might be a third variable causes both, or it could be coincidence, especially if you had a small data set. And the mathematics is not going to tell us which of these are the case. It's not. You just have to think about what makes sense in the situation. And this example here, a study of public school students ages 5 to 18 years old showed strong positive correlation between the number of cigarettes smoked per day and lung capacity. In other words, the students who smoke the most cigarettes tend to have the largest lungs. You might think, well, smoking increases lung capacity. If I want bigger lungs, I should smoke. Or maybe people who have larger lungs tend to smoke more. Maybe having larger lungs causes people to have a craving for cigarettes. But the thing that makes the most sense here is that the increased age would affect both, because the age range here went from 5 to 18 years old. The 5-year-olds are not fully matured. They're going to have smaller lungs, not because they smoke or don't smoke, but because just because they're not fully developed yet. They're younger, and the 18-year-olds, teenagers tend to smoke, and they also they're more fully developed. So the increased age probably affects both the amount of smoking and also the lung capacity. Another possibility that could happen would be a coincidence, especially if you had a small data set. But this was actually a pretty large study. I think there was about 2,000 students in the study. So anyway, just be cautious about jumping to conclusions about cause, and think about what makes sense in the situation. And that concludes this presentation.